Now let's deal with the aperiodic example. In the aperiodic example, is discrete time Fourier transform. This is n, and we have 1 guy, 2 guy, 0, 0, 0, 0. And we now see that my x of n is aperiodic, discrete time. And only is interesting at 0, 1, and for 2, 3, 4 onwards, and -1, -2 onwards, all values are 0. And if I've ever given you this kind of graph, then life becomes very easy, because you're only going to deal with the 2 ones standing up. The rest of the 0 later on will cause every other partial sums to disappear. What am I talking about? All right, let's perform the analysis. In the analysis, it means I break x of n into complex exponential. In the DTFT case, the notation is capital X, small e j omega. The equation's summation of the sequence x of n across -infinity to infinity, because he is aperiodic, and therefore you have to take all his sample, e minus j omega n. And this is the analysis equation. And it looks very complicated, because in your mind, you have to do this. Not only that, you have to do this. You have to deal with this. And what is omega? Omega is the angular frequency of the complex exponential, and omega is real. Can be any frequency. And in fact, later on you realize actually I'm cheat you. He's real, but he's periodic, 2 pi. So we are interested in omega from -pi to pi, or 0 to 2 pi, whichever you prefer to draw. Now, but what this means is that to analyze this equation, I have to deal with infinite sum of xn multiplied by e minus j. I have to plug in all values of small omega. And therefore, it looks like it's impossible to deal with this. But let's try in this very simple example. Let the number here be 2. And if you look at this xn very carefully, you see that everybody is 0 anyway. So if you have to write this down, it is only interesting at x0, e minus j omega. This guy is n equals to 0 plus x1 e minus j omega. This guy is 1. And the rest are 0. And we're not interested in them. And now let's plug in x0 and x1, which is 2. And e minus j omega 0 becomes e to the power minus j omega 0 is the number 1, right? E to the power of minus j 0 is 1. So the only interesting thing is 2e minus j omega. And now you have the closed form solution of x e j omega. So in this kind of very simple example, because the number of values in my aperiodic sequence is finite, I can very simply and very quickly write down my discrete time Fourier transform. And then what do you do? What is the discrete time Fourier transform? What does this mean? So what should you do? Remember, what is x e j omega? it is a function with respect to omega. So I'm going to draw omega here. And here, let me ask again, xej omega is a real number or a complex number? Look, this is a real number. This guy, 2 is still a real number. E minus j omega is a real or complex number? Complex number. So real plus real times complex is complex number. So out comes a complex number. Okay? So for a complex number, I have to represent as its magnitude and his phase. Okay? Now, so what about x? Okay, let's plug in omega equals to 0. So what is x? E j omega equals to 0. This is equals to 2 plus 2 times e minus j 0. Answer is? Right? Agree? And therefore now at omega equals to 0, out comes the number 4. And then I keep on plugging in different values into this equation. And then as I vary my omega equals to minus pi to pi, I will plot the graph. Can you all see? Okay? And if you do this, you have just plot the discrete time Fourier transform of this signal. Alright, go and practice. It will be helpful in the exam. Alright. Now, I've showed you the analysis equation. You will now realize that x e j omega is periodic. Okay? Later on, if you plot x e j omega, it is always periodic with 2 pi. That's one. 2, it is continuous. At every value of omega, real, there is x e j omega, a value. He is unlike the discrete time Fourier series, which the coefficients of the analysis are at discrete frequencies at k, where k is 0 to n minus 1, or if you sometimes think k is at k, multiplied by the fundamental frequency 2 pi over n. Alright, but in this particular case, our friend here is continuous. So trying to reconstruct xn is a bit hairy. We have to use an integral because our friend x e j omega is continuous. First we use a normalized constants 1 over 2 pi, integrate over 2 pi interval x e j omega e plus j omega n d omega. And this is the discrete time. This is the discrete time Fourier transform, the synthesis equation. Or sometimes we call this the inverse discrete time Fourier transform. Alright. So if you have this, and just now we have this, then theoretically you can get back your sequence.